Okay.
All right, so this graph is showing us, if we notice here on the left, the membrane potential. And if you remember from the lesson, there was an easy word that I told you to trade out for potential here. What was do you remember the word I told you to pretend that potential is?
Actual potential is the movement. I don't know if this was this word or not.
Yeah, so an action potential is a moving version of this. That word potential, what I kind of told you to sub it, whether it's an action potential or membrane potential, sub out the word charge, or pretend like whenever you see this word potential in our class, we're always going to assume that it means, like you mentioned, we talked about an action potential with muscles, and we have that with neurons too. An action potential is a change that moves, like you told me. This graph here is showing me the membrane potential, which basically is just telling me what's the charge on the membrane when various things are happening in the neuron. So at the beginning of our graph, here at the very beginning, and also over here at the very end of our graph, our neuron is at its normal charge. When we look over here on the list of potential labels, which of these labels over here means that it's the normal charge of a neuron?
It's going to be in dendrites.
Well, so it would be what I call the normal charge in the dendrites. This is what happens in the dendrites. Before the dendrites get a message, their membrane charge is down here at -70 millivolts, and we end up at -70 millivolts when we're done responding to a message. -70 millivolts, it has a special name in neurons. I call it the resting membrane potential. So the resting membrane potential is the normal charge on the membrane at rest. So I'm going to abbreviate here because that's a long thing to type. Resting membrane potential. At the very beginning of the graph, this is my normal charge on a neuron. And the normal charge on a neuron is -70 millivolts. It's going to chill out at -70 unless it gets a message from a neighboring neuron. If it gets a message from a neighboring neuron, especially an excitatory message, that's going to cause its membrane charge to get more positive, like we see here. If we get positive enough, we're going to hit a special value that's going to cause my neuron to freak out and go talk to its neighbors. Do you remember from my list of options over here what the name was of that special value that if I hit it, my neuron is definitely going to go talk to its neighbors?
Threshold.
That's right. Yep. So the threshold value is what I see right here on my graph. And what I'll mention with neurons is we do need to know a few numbers. I don't always ask you to learn numbers in our class, but we do need to know the neurons here, or the numbers here on our neuron. So we need to know that the resting membrane potential is -70 millivolts. That's where I start, where it's normal. And we need to know that the threshold value is -55 millivolts. So in other words, if I get this much different, if I'm 15 millivolts different from normal, that tells my neuron, hey, there's something going on here. I need to talk to my neighbor. So up here at the very top of my graph, this is when a neuron talks to its neighbor. The way that a neuron talks to its neighbor is it spits out something. What do neurons use to talk to each other? What do they spit out?
Neurotransmitter.
Exactly. Yep, neurotransmitters. So up here at the top, this is where I have neurotransmitter release, where my neuron is going to spit out messages that it can then send to its neighboring cell. So let's review what we talked about so far. We have our basic normal membrane charge called resting membrane potential. That's -70 millivolts. Then we have this part on my graph right here called threshold. Threshold is when my membrane charge changes just enough, I'll get to -55. At -55, my neuron is committed to talking to its neighbor. And when it gets all the way up here, the last number we need to know is +30. all the way up at positive 30 is when I'll spit out neurotransmitters that allow me to talk to my neighbor. So we have two parts of our graph here to label that are kind of mirror images of each other. This part over here on the left is when the membrane charge is going up. When the membrane charge goes up after we've hit threshold, what do I call it when I make my membrane charge more positive? What's this side of the graph?
Depolarization.
Exactly. Yep. Depolarization.
Polarization. Okay, depolarization.
Depolarization means we're going away from our normal value. So depolarization means the charge goes up. Depolarization is what helps me to get from threshold all the way up to where I will release those neurotransmitters, all the way up at positive 30. The thing with a neuron, though, is once I hit positive 30 and once I spit out my neurotransmitters, the neuron has a moment where it's like, oh, my membrane charge is completely wrong now. I'm positive 30. I should be negative 70. I need to get negative again. I need to go back down to my normal charge. The process more negative to kind of try to get me back to where I should normally be. That process is called repolarization. Repolarization, the goal is to get back to normal. That's what I'm hoping to do in repolarization. But if you notice this part of my graph over here, I actually go, so here's negative 70, right? Here's normal, where I should end up. Because fast to repolarize its membrane to try to get it negative again, I actually get a little too negative. So this last part of my graph down here is called hyperpolarization. And in hyperpolarization, it's just like when something is hypertonic, where there's too much. When my membrane charge is too negative, like I see right here, I call that hyperpolarization. So my neuron gets so excited to get back negative that it gets a little bit too negative, and then over time we're going to get back to normal, back to the resting membrane potential. So the first thing that we need to know with this graph is we need to know the names of each of these parts of the graph. So we need to know that resting membrane potential is my normal charge when I'm at negative 70. We need to know that threshold is the charge where I'm going to decide to send a message. If I get here, if I get to negative 55, that's threshold. At that point, it'll allow me to do depolarization, where my membrane charge goes up really fast. I'll spit out neurotransmitters at the top, but then I've got to get back negative. Oops, I went a little too negative. Eventually, I get back to normal. So the first graph that you have to label there on page 12, we learned those names. That's going to help us when we go to page 14. And now we have to talk about the specific kinds of channels that I use in each of these places. So here's our list of options for the kinds of channels that we're going to see on our graph here. I want to start with underlining a few things. I want to underline, notice that this one's called a chemically gated channel, and these ones are called voltage-gated channels. Can you remind me, when we talk about a chemically gated channel, what opens up a chemically gated channel?
For the chemical gate, they need some signal.
Yeah, and so what did we say was the name of the kind of signal that neurons use to talk to each other?
Neurotransmitter.
Exactly. Yep. So the chemically gated channels that we have on this graph, chemically gated means I open with a chemical. In this case, it's a specific chemical, so we open with neurotransmitters. We open with neurotransmitters if we're a chemically gated channel, because neurotransmitters are an example of a chemical. So some of the channels on our graph are chemically gated channels, meaning they're going to open up with chemicals, with neurotransmitters. Some of the channels that we're labeling on our graph are voltage-gated channels. When I talk about a voltage-gated channel, what opens up a voltage-gated channel?
I can't explain.
Do you remember what the word voltage meant or what it
They
kind of
need
referred to?
they need yeah, I remember from the one of our works, they need a gate. It's like a gate. You need to be able to open. You need some help, like someone needs you just to push it.
Yeah,
I don't know
so
if
the
I'm right.
pushing kind of gates, those were the mechanically gated ones. The ones that we said we needed a chemical key for, that was these chemically gated ones. Our last type, the voltage gated ones, those were the ones that opened up when the voltage changed, or they open with a charge changing. So the voltage part means that it has to do with the membrane charge. If we have the normal charge, if we're at negative 70 like usual, a voltage gated channel is going to be closed. If our membrane charge gets too high or it gets too low, we change the voltage enough, that's going to open up these channels. Where voltage gated tells me that the way I get these kinds of channels open is when I change my membrane charge enough to open them. The word chemically gated tells me that I use specific chemical keys. In this case, we're talking about neurotransmitters to open up those channels. When we talk about the chemically gated channels that open with neurotransmitters,
It's gonna be when
the,
they reach the thresholder.
yeah, that's going to help us get to threshold, actually. So my
I know.
chemically gated channels are actually, I'll circle it here, and then I'm going to put a little abbreviation. This part of my graph right here, the very beginning part, that's where I see those chemically gated, actually I'm going to abbreviate, chemically gated channels. Chemically gated channels are what I use to change the charge on the membrane. So I start down here at the resting membrane potential, and what gets me up to threshold, what gets me to negative 55, are those chemically gated channels. So at the very beginning of the graph, this is where neurotransmitters have an effect on the charge of our membrane. So those neurotransmitters, when I receive them and they open up the gates, that's what's going to get me to threshold. Threshold is negative 55. So it's a charge that's different from negative 70. So at threshold, I'm going to open up a type of voltage gated channels. Do you happen to remember which kind of voltage gated channels open at threshold?
Potassium? No, sodium.
Yes, sodium, voltage gated sodium channels. So voltage gated sodium channels are what open up at threshold. And here's a little reminder for us here. I'm going to draw my little cell. When we talk about a cell, the ions that we care about, inside versus outside, are going to be potassium, sodium, and we're going to add chloride. Potassium, sodium, or chloride? Which one do I have a lot of inside a cell? Do you remember?
Potassium.
A lot of potassium. Yep, lots of potassium inside. Okay. And on the outside of the cell, we've got a whole lot of sodium, and we've got a whole lot of chloride. Both of those are on the outside of the cell. That's important because I'm saying this is a voltage-gated sodium channel. So a voltage-gated sodium channel, it opens when I hit threshold. And actually, I'll draw an extra line for us here. Voltage-gated sodium channels are what help us do the process of depolarization too. So it's in two places on the graph. It opens at threshold, and it's going on throughout this entire process here. So my voltage-gated sodium channels, when I open them up, they're going to go from the place where there's a high concentration, which is outside the cell, to the place where there's a low concentration, which is inside the cell. So when I open up a channel for sodium, sodium rushes inside my cell. And remember that sodium has a positive charge. So when I open up this channel for sodium, I bring a bunch of positive charges inside the cell. That's why when I open these channels, see how they make my membrane charge go up, up, up really fast. So voltage-gated sodium channels open when the voltage or when the charge is wrong. And when they open, they bring sodium inside, which makes the membrane charge get really positive. Up here at the top of my graph, we're at positive 30 now, positive 30 millivolts. Technically, there's two kinds of channels that open up here. One of the channels that opens up here is the kind of channel that its only job in this process is to help me spit out neurotransmitters. Do you remember, was it calcium or was it potassium that helped me to spit out neurotransmitters?
Calcium.
It's the calcium. Yep. So up here at the very top, we open up voltage-gated calcium channels. Voltage-gated calcium channels. The job of a voltage-gated calcium channel is to release a bunch of calcium into the neuron and neurotransmitters. So at the very top up here, remember these are voltage-gated. Voltage means it's a charge problem. So when I get all the way up to positive 30, my neuron says, oh, I'm supposed to be talking to my neighbor. I'm going to use calcium to help me to talk to my neighbor. So up here at the very top, we open those voltage-gated calcium channels. We also open up the same kind of channel that helps us to do the process of repolarization that I see going on over here. Which kind of channel helps me to bring my membrane charge back down to normal? What's on this other side?
It's going to be potassium.
This is where I use that potassium, voltage-gated potassium channels, voltage-gated potassium. Our cell picture over here. I've got a whole lot of potassium inside the cell. I don't have nearly as much outside the cell. So when I open up a channel for potassium, potassium leaves. And when I pull out these positive charges from inside the cell and make them go outside the cell, that makes my membrane charge more negative because I'm spitting out positives here. So I use voltage-gated potassium channels to bring my membrane charge back down to where it's supposed to be. But remember, we talked about how we did hyperpolarization. We went a little bit too negative. To get back to normal, to help me return to this normal space, this is where I'm going to use those leakage channels. Very end.
Okay.
When we talk about those leakage channels, remind me, leakage channels are or are not always open. Do you remember? A leakage channel. They are always open. Absolutely right. Yep. These ones are always open. That's why they get their name leakage, because they're constantly leaking. So I'm going to leak potassium and sodium to get me back to normal until I'm all the way back at resting membrane potential.
One question. Okay, this one, that's the leaking channel, they are gonna happen after the hypolarization, yes, because they are trying to get the membrane back to the resting potential.
That's correct. Yep. The job of a leakage channel is to get us back to resting membrane potential. Here, I'll put a note about that. Goal, get to resting, let's go underneath it, membrane potential. That's their one job. The leakage channels, their one job is to get us back to resting membrane potential. When we talk about the voltage-gated potassium channels, remind me, what did we say this was called right here, where we made the membrane charge negative?
The repolarization.
Yep, so let's put a note there. Goal of these is repolarization. But they also cause hyperpolarization. They're so good at their job that they actually make us too negative. So their goal is to just repolarize us, but they accidentally send us to negative, hyperpolarization. Leakage channels, their goal is to get us back to resting membrane potential. What did we say was the job of the calcium that we brought into the neuron? What did that help us to do?
The calcium is going to help to release the neurotransmitter.
Exactly. Release neurotransmitters. And what did we call the process on the left side of the graph where we got more positive? What's this process called right here?
This is depolarization.
Exactly. So goal of my voltage-gated sodium channels is depolarization. So I'll draw a little line. That's the goal of these guys. The chemically gated channels, I mean, I guess we could say that the goal of a chemically gated channel is to get us to threshold, but this is also, when you think about the chemically gated channels, the big thing to remember with them too is these are the kind of channels that are directly responding to messages. So if my messages are excitatory, meaning I'm supposed to tell my neighbor, that gets me to threshold. If I happen to be receiving a message that's inhibitory, that's not going to help me get to threshold. So my chemically gated channels in general, if we're thinking about what they can do to a neuron, their goal would be to get it to threshold, but chemically gated channels do also receive messages that make it go away from threshold too. So keep that in mind when you're thinking about those chemically gated channels.
Okay. I have, in one of my graphics, I wrote here on the resting, let's see, on my resting potential, I wrote that they have the leak channel, like a pump, sodium and potassium pump. They begin.
Yes.
Okay, then it's right.
Yes, so we use that. That's actually the big picture purpose of the sodium potassium pump. Its job is to establish. Yeah.
Right, then,
so that is correct.
Beginning, not only the end.
Yeah, so it would be in both places. Yep, we would see that over here helping us to get to resting membrane potential. We would also see it over here to help us stay at resting membrane potential.
Okay, I got it. Yeah, I don't know. I changed number here on gate and chemical gate channel. I wrote leak channel. I got confused.
Yeah.
I didn't know. I said, okay, I was confused. That's why I couldn't understand. I couldn't find the answer for everything. Now I'm more clear. And I have one more question. It's going to be the last one.
Okay.
It's going to be for page 15. And the question was, when does the absolute refractory period start? I'm confused if it starts on 70 or 55. Here in the graphic, they are showing, I guess it's 70.
So what I would say is we don't necessarily have to think of it as a value as much as what I would say the best answer for this question is this right here. So the absolute refractory period begins when a neuron gets a stimulus, or in other words, when it receives a message, because the way that a neuron's membrane starts to change is it has to receive a message, and that message has to open up its chemically gated sodium channels, which will open up those voltage-gated sodium channels. So when a neuron receives one message, it can't respond to another message at the exact same time. So what I would say to answer this question, when does the absolute refractory period begin? I would say it begins when a neuron first receives a message. When the neuron gets a message, when it gets this stimulus, and when it starts to respond to that stimulus, it can't get another one until it's back down here and it's into that relative refractory period, or more likely until it's over here back at resting membrane potential. So technically you could say that it's somewhere between -70 and -55 when it's in that charge range, somewhere in there. But I think the best answer for it is the absolute refractory period starts when it first gets a message. When it's responding to another message, it can't respond to the one that you're trying to send now. So between 70 and 55, somewhere in that range.
Okay, and when they end, I think my answer is wrong. I put threshold and I looking at the graphic, I don't know.
Yeah, so
Why?
when you got that from the guided lesson, and I would say that is correct. When we talk about when it gets back down toward the threshold value, so keep in mind the absolute refractory period, when we first hit threshold for the first time here, I'm still in the refractory period. We go all the way up here, and then when I start coming back down, and then I get close to the threshold value on my way back down when I'm doing repolarization, this would be the point where I probably enter the relative refractory period. So I'll make a note. During repolarization, when we hit threshold. When we get back to -55, that's about when we would enter that relative refractory period. It has to do with the kind of channels that are involved in making us do this process right here. So let's remind ourselves here, my membrane charge is going up really fast on this side of the graph. What did we say again was the name when I make my membrane charge go up? What was that called?
Repolarization? No, depolarization.
Yeah, so when it goes up, it's depolarization. So depolarization is when my membrane charge goes up. Do you remember, because we labeled this on our graph, which specific kind of channel did depolarization? Which kind of ion channel did that?
Voltage gate sodium.
Exactly. Voltage-gated sodium channels. Okay, so this process of depolarization that's happening on this side of my graph, it is done by voltage-gated sodium channels, which means that what opens them or what closes them is charge. I need voltage-gated sodium channels to allow me to depolarize my membrane so that I can send a message to my neighbor, so that I can respond to a message. If I'm in the process of responding to a message right here, I am not going to be able to respond to a new one. These channels, if you remember from your other picture, voltage-gated sodium channels, not only closed, they also have that state where they're like blocked. Remember, it kind of looks like a ball and chain where it puts that little ball inside and then it can't respond because it's all tied up. It's deactivated. Well, we get back into the right shape right around here, around threshold. So when I'm back to a shape where a voltage-gated sodium channel could open up again, I'm to the right voltage, which is right around threshold, then I potentially do another signal. Remember, that's what relative refractory period means, that I could respond to something, but it needs to be a really strong message. So once my voltage-gated sodium channels get back to the right shape, once that little stopper pops out, that's right around threshold down here. At that point, we get into the relative refractory period, where I could maybe respond to another message, but remember, it has to be a really loud message. You're gonna have to work a little bit harder to get me there.
Okay, I got it. Hello?
I'm still here. Yep.
Okay, that was my question. You answered it. Thank you.
Yeah, you're welcome. And if you think of others, please feel free to reach out. We have until Friday on this lesson, although I'd recommend trying to get it done before then, since you've got another one due Sunday. So
Yes, yeah, I finished this one and I'm going to my lab and then I'm going back to the other lesson.
sounds good.
So, okay, thank you so much and have a good day.
Yes, you as well.
Bye.
Bye.